Hi everybody, it's been a few weeks now since my last YouTube video. Over the last couple of weeks I've been having another look at the electronic DC load project and taking into account a lot of the feedback I've had from you. I had some particularly good feedback from Kenneth Laverson, who pointed out one or two little issues we had with the project, so I'll try and implement them as well. So that's what we're going to do today. I also thought I'd take the opportunity of trying to redesign the printed circuit board, just so we have one PCB where all the elements are on that board, because as we've built up this project, as I've added new features, I've been adding additional little PCBs to the main board. So that's something else we're going to have a look at today. I will actually say that if you've been following this project from the start and you've been building it as we went along and you've built on the little modules as we went along, all of the modifications and improvements I'm going to discuss today you can actually add to your existing project just by making some changes there. So I'll try and give you as much detail as possible. There will be some downloads as well which will help you. So let's get on and have a look at part 7 of the electronic DC load. Right, well let's have a look at some of the updates I've added to this project today. I've highlighted a few of them here on this simplified diagram in red and green so we can see them quite clearly, and I'll go through and explain each one in turn. So if we take the first one there where we've got two diodes on the output of the DC load, and that's in series with the fuse, and the reason behind that is I wanted to give a degree of protection in the event if you applied a load in reverse. So if you applied the negative of the load onto the positive terminal, in order to prevent any damage we can put some blocking diodes in there, DC blocking diodes, and for that I've used a dual power diode which comes in a TO220 package. It's capable of handling up to 40 amps at 100 volts, so it's ideal for our purposes. And because we've got two diodes in one package, I'm simply going to strap them in parallel. The cathode is already common on the device, so we just need to strap the anodes together and we can increase the amount of current it can handle. So that's the first change I've made, and that is added just before the 5 amp fuse. Now the other thing I've added is some offset null for the op amp that's driving the power MOSFETs. I've just simplified the diagram here for the power MOSFET output stage there. I'm not showing the other transistors and the little protection circuit I built, but this is just to illustrate the reason for having the offset null, which I've shown here in green. And what we found is that we could never quite get the current down to zero. There was always a few milliamps, even though the current was set to zero. We always had a few milliamps flowing through the MOSFET and the load. And what I want to do here is ensure that at zero it's actually zero current going through the load. And to achieve that I'm having to apply some offset voltage to the that op amp there, and the simplest way of doing that is applying a voltage to the negative input of the op amp through a high resistance. I've got a 4.7 mega ohm resistor there, because we've got no current effectively flowing there. We just need to apply a offset voltage to the negative pin so we can trim it down and ensure that when we've no current then that is at zero. And to do that I've used a 10k preset, and we have to have it across a very stable voltage supply of both a positive and negative voltage. So I've put the top end of the preset to the 4.096 volt reference, which is very stable, and we're going to create another very stable negative voltage, which I'll show you shortly, of minus 2.5 volts, and that's the other end of the 10k preset will go to that. So we can trim that between a positive or negative voltage and apply some offset voltage to the op amp there to compensate for any offset error in the op amp, and we can trim it down so we've got no current flowing through the load. So that's the first modification there. The next thing I've done is added some trim for setting the actual current that's driving the MOSFET. Now you remember that what we did originally, we had the voltage coming from the 12-bit DAC through a buffer, and then it was applied across a potential divider which divided it down by a factor of 10. So we had a 9k resistor and a 1k resistor, what I've done now is I've changed that 1K precision resistor to a precision 909 ohm resistor and added a good quality 200 ohm preset in series with that. So we have some trim there now. So what we can do is, once we've set everything up, we can make an adjustment there to ensure that the actual current that's applied there on the DC load is accurate by having some degree of calibration there. So that's the second change I've made to this diagram. Now the third issue we had, which was highlighted by a couple of my viewers, is that if you happen to have a load connected to this electronic DC load at switch on, just for a fraction of a second or two, you get between 1 and 2 amps a surge going through the load, and then it goes to 0. And the reason behind that is it's due to an issue we have with the 12-bit DAC. This particular 12-bit DAC is the MCP 4725. It has a built-in EEPROM memory, and within that memory, during manufacture, they set a default level for the output at reset at switch on. And what they've done is that they've set that reset default setting to half the supply voltage. So what that means is that when we just switch on the electronic DC load, immediately at switch on, the 12-bit DAC, although we've got no signal there saying this is the current, the output is reset to half of the supply voltage. Now in our case we have a supply voltage at 4.096 volts, and what will happen there at switch on, just for a second or two, the output of the DAC will give us about 2 volts there on the output, which is fed then through the buffer to the voltage divider network there, divide by 10, and we're then going to get about 0.2 volts immediately fed onto that op amp. And what that's going to do is drive the MOSFET in such a way that we're going to get about half the maximum current. So we're going to get about 1 or 2 amps flowing through the power MOSFET and the load at switch on for 1 or 2 seconds until the 12-bit DAC has reset itself and received the information in terms of what the output should be. So that's a little niggle that we have with the circuit. It's not normally an issue, and in fact I didn't spot the problem until it was pointed out to me, because I would normally not connect a load on the output there before you switch on. So I'd switch on first and then connect the load, so you'd never see that. But I thought we'd have a look at overcoming this problem in the event of you having a load connected at switch on. And the simplest way of overcoming this is to prevent that 0.2 volts there at switch on causing a drive voltage to the MOSFET, and the easiest way is to provide a similar voltage of around 0.2 volts or more onto the negative input of the op amp, and that would compensate for that, and we'd get 0 coming out. So what we're going to do here is use a little circuit I've put together using a NPN transistor, and what we're doing here is that at switch on we have a CR network there, the capacitor at the top end going to the plus 5 volt supply, and immediately at switch on that capacitor's got no charge on it. So at switch on, both sides of the capacitor will be at supply voltage at 5 volts. So at switch on, you find you've got 5 volts on the base of that transistor, turning it hard on, and then supplying then the 5 volts through a 100k resistor to the minus terminal of the op amp there, and providing a positive voltage there on the negative input. Over a few seconds that capacitor starts charging up, and when the capacitor becomes more or less fully charged, or just before, that transistor turns off and removes that voltage from the op amp. So that circuit is now isolated, having no effect on the op amp. But just for a few seconds at switch on, it's generating a positive voltage there to counteract the positive voltage on the positive input, and ensuring that the output of the op amp is not driving the MOSFETs. Now what I've also done is added a diode there, the 1N4148 little switching diode, from the bottom end of the capacitor to ground, and what that does is that when we switch the DC load off, then that capacitor, that 10 microfarad capacitor, will actually discharge very quickly through the low impedance path of the supply rail. and that ensures that if you happen to switch it on again, quickly again, this little circuit will operate for about 1 or 2 seconds and do the same job again and prevent the output of the op-amp driving the MOSFET. So that's that little additional circuit there we've applied. Now, what I have realised is that there's actually a means of reprogramming the EEPROM in the 12-bit DAC. But yeah, I'd have to have a little program that we use before we load the main program and just run it once. And I might have a look at that later, because what we could do is we could reset the default setting in the 12-bit DAC. Instead of saying at reset set the output to half supply voltage, we could say at reset set the output voltage to 0, and that would probably overcome this problem. But that's something I'll have a look later and see whether we can also do it in software. But for the meantime, we've got this little circuit here which is compensating for that problem and ensuring that the load is not supplied with any, we're not getting any current going through the load at switch on. So there's the first few changes that we've made to the project today. I mentioned that we're now going to need a negative 2.5 volt reference for our little nulling adjustment that I've applied on the main board, and for that I'm going to use the LM431. It's a little IC in a 3-pin TO92 package. It's got an adjust pin there, and the reference voltage is in our case coming out from the anode, because we've got it that way around to give us a negative voltage. And depending on what you set the adjust pin to determines what the output voltage will be. Now, that particular device has got an internal 2.5 volt reference within it, and if you short the adjust pin directly to the cathode, it sets the output reference to exactly that voltage of 2.5 volts. And what we're doing here is we've got a 2.2k resistor there, which is supplying sufficient current to that device to give us a nice stable, in this case minus 2.5 volt reference that we're using for our nulling circuit. So that's the other little modification I've had, and we're supplying that circuit from our negative 5 volt supply, which we have already, where we've been using the ICL 7660. Now, while I was looking at this circuit, I did have a look at trying to improve the stability of that voltage, that minus 5 volts. We never actually got right up to the minus 5 volts due to the efficiency of the IC there. So I thought, let's have a look at ways of improving that. And I realised that when I was doing that the capacitors that I originally had there, I just used normal electrolytics. But for this device to work well, you need to have low ESR capacitors in there. And for that, well, I've replaced these two now for 2 solid tantalum capacitors. That improved things slightly, and we got the voltage there increased a little bit, nearer to the minus 5 volts, but it was still below the minus 5 volts. So the other thing I tried was altering the switching frequency of this device. There's actually an oscillator pin comes out at pin 7, and if you were to simply connect a capacitor from that pin to the plus 5 volt supply, and you add in a 100 PF capacitor there, it'll reduce that frequency down to about 1 kilohertz. Now, normally that frequency is running around 10 kilohertz, so by adding that capacitor you're reducing it by a factor of 10. But if you were to do that, the switching is now a slower speed, and to compensate that slower speed, you also now have to increase the values of those 2 capacitors by. So you need to increase the value of those 2 capacitors to 100 microfarad tantalums as opposed to the 10 microfarad tantalums. And that little arrangement did work quite well, and again the voltage edging even closer to our minus 5 volts. But I decided to look at another alternative, so I got rid of the capacitor, even though there's provision on the PCD if you want to try that. The other option is look for a better switching IC than we've got, DC switching IC that we've got there. And the one I found was the LTC 1046 from Linear Technology. It's actually pin compatible with the ICL 7660, but it's actually more efficient, It's also capable of providing 2.5 times the drive capabilities, current drive capability of this original IC. So I just simply unplugged that chip and then put the LTC 1046 in its place, and keeping the same two 10 microfarad tantalum capacitors, the output voltage then edged a little bit closer to the 5 volts, and I was getting around about minus 4.97 or not 4.98 of a volt, which is getting virtually close now to minus 5 volts. So I settled on that, simply swapping that IC for the LTC 1046. But the choice is yours. If you're using that, you can continue using that IC, but if you want to improve it a little bit, just swap it for this chip here. Now, one other update I've made to the project is to overcome the issues we were having with the offset voltages of the op-amp buffers there that are driving the ADC, the MCP 3426. And what I found is that the voltage sense going in on one or the current sense going in on the other, we could never get down to 0 going into the ADC. There was always a very small voltage going into the ADC, even though the voltage sense was telling me it was 0. And equally with the current, if the current was saying 0, we still had a very small voltage going into the ADC. And in the past, what I did to try and correct that in software was give a little calibration facility where we would calibrate it at switch on to null out these small voltages, and then we'd subtract that from the voltage reading. But another way of achieving this is to ensure that the voltage going into the ADC when the voltage sensor, the current sensor at 0, is to make sure that pins 1 and 7 of the ADC are capable of going down to 0. And one way of doing this is feeding that point there to a negative 5 volt supply. And since we already have a negative 5 volt supply, I found that if we take that on the voltage sense line there through 180k resistor, the 5 volt negative 5 volt line, that ensures that that pin there is capable of going down to 0. And on the current sense pin there, pin 7, a similar thing there, but this time I'm using a 2.2 mega ohm resistor to the negative 5 volt supply, and that just ensures that the voltage there can be driven down to 0 when we have the current sense should be reading 0. So just adding 2 resistors and feeding them to the negative 5 volt supply ensures that when we switch on and we have no voltage and no current, that what's going into the ADC is such that the ADC output onto the I2C bus feeding the Nano is reading 0. So that's the other change that I've made to the circuit. Now, one other thing I thought we'd have a look at, since we're looking at some updates, is the I2C bus. And I just want to illustrate that the I2C bus that we have, which is coming from the Arduino Nano, we've got quite a few items now hanging on that bus. We've got the LCD module, the ADC, the DAC and the real-time clock. All of those elements of the circuit are adding additional capacitors onto the I2C bus. And what that does is that as you add more capacitors loading onto that bus line, it tends to actually increase the signal transmission time, so it slows things down. So it slows the speed down of the addressing those devices, which is not particularly good. And that's caused by the CR time constant on the I2C bus of the capacitance loading of that and the actual length of those lines as well, and the value of the pull-up resistors. Now, we can do very little about the capacitive loading of these devices that we're using on the I2C bus, and although we can make a few improvements on the printed circuit board layout to reduce the length of the I2C bus line, but the easiest way is to reduce the value of the resistors, the pull-up resistors. So if we were to reduce the value of the pull-up resistors, that will compensate for some of the effects of the increased capacitive loading we have there. And what I'm going to try today is to replace the 10k resistors with drop them down by about half. So we're going to put 4.7k pull-up resistors in there for R19 and R20, and what that should do is overcome some of the effects of the loading, capacitive loading we have on these devices. So that's one thing we're going to do. The other thing with the Arduino Nano, when we initialize the I2C Bus, we use that command in our code, which is wire.begin bracket bracket semicolon. But what that does also is it sets the default speed of the I2C Bus in the Arduino to 100 kilohertz. So I thought, let's have a look at seeing if we can increase the speed of the I2C Bus to speed things up a little bit, and see if we can get up to 400 kilohertz. So I'm going to go to 400 kilohertz, and I believe that we can do that with a software command, which I'm going to try. And what we do is we add another command directly after the wire.begin command. So we add wire.set clock with a capital C, open brackets, 40000 L, close brackets, semicolon. And what that will do is it will set the speed of the I2C Bus to 400,000 Hertz, 400 kilohertz. So I'm going to give that a try as well. If you increase the speed of the I2C Bus, then you've also got to ensure that the loading on the bus line is also improved. So those resistor reduction values there are going to help that situation as well. So two things we're going to do, or at least try, is lower the values of the two pull-up resistors and try and increase the speed of the I2C Bus up to 400 kilohertz by adding that command there onto our code. Another small change I've made to the project is in the output stage here, where we've got the power MOSFETs. And remember, we had these transistors here giving some protection to prevent them the power MOSFETs going into thermal runaway. And if you recall, we had the emitters of each of those transistors joined together and then going through one 47k resistor to the minus 5 volt supply. I found that if we put an individual resistor return in each of the emitters of those 4 transistors now, and then take it to the minus 5 volt supply, this particular circuit does work a little bit better. So that's just a minor change I've made, adding the additional 47k in the earth return of each of these transistors Q6 to Q9. Here we see a few other minor changes we've made to the circuit. Remember, originally the fan control was using data pin 2, but unfortunately data pin 2 cannot give us pulse width modulation output. Even though we had our software trying to drive that, it was simply turning the fan on and off. So to correct that problem, I've now moved the fan control to data pin 3, which means we're now using data pin 2 for the rotary encoder. I'll just swap those two around. The only change really is in software. We simply alter the references to these data pins in software to reflect this change. The other change I've made is I've moved the output from the temperature sensor that was originally going into the analog pin A0. I've now moved that to A6, and again I've made the appropriate change in software to reflect that. That frees up analog output pin A0, which can handle both input and output signals. And the reason behind that is I wanted to free that up for a future upgrade, possibly having constant voltage control. We might need to use that.
I've produced a new design PCB for part 7 of this project, and the artwork you see here on a transparency, I'll make this available to you as a download, so if you wish you can produce your own PCB. I've designed it as a single side board, and so to accommodate that I've got a number of links, jumper links on the top of the board. Here we now see the new printed circuit board I've put together for part 7 of this project. I've now incorporated all the previous separate little modules we had onto this one PCB, together with the main element of the DC load. The surface mount ICs are all mounted on the print side of the board, and pin 1 is indicated by a little round dot. Be particularly careful when you're putting the smallest of the surface mount ICs on, which is, there's one in that location there and one there. They're very tiny SOT23 type packages, and just be careful that the pins on the PCB are not shorting or running into each other. You may just have to scratch away once you've etched the board if you find that it's not etched away cleanly. Well, I think what we'll do next is we'll mount the components on the board and we'll put it to the test. Here we now have all the components mounted on the new printed circuit board. The Arduino Nano is mounted in inline connectors there. I've mounted on the PCB, and then the rest of the inputs are all socketed. Now we've got two additional preset trimmers there on the board. This little one here is the one we're going to use to offset the null so we can get the output current to 0, and that one there is going to give us a bit of trim on the drive voltage for the MOSFET so we get the correct current. So they're the two additional ones. Just point out a few other items on the component side of the board. There we have the Darlington transistor, which is driving the fan. Once we've soldered that onto the board, then I've just bent and folded that down to keep it out of the way of the socket there for the USB lead for the Arduino Nano. The other ICs on top of the board, we've got the IC there, op amp for the voltage sense input circuitry. There's the DC converter charge pump chip, which is giving us the minus 5 volt supply. That's the LM431, which is giving us the minus 2.5 volt supply there. Down here we've got the opto coupler there, which is part of the input trigger circuitry. And there you have the preset, which is altering the timing of the trigger pulse, and there's the preset where we can null the input voltage sense circuitry. So they're the main points on the PCB. I've actually got little test pins in some convenient places where we can do some tests. I've got a test pin for the minus 2.5 volts, a test pin there for the minus 5 volts, a test pin here for the plus 4.096 volts. There's a test pin there just so we can check the drive voltage going to the output stage, the MOSFETs. And on the input of the power supply side, we've got the 5 volt plus 5 volt test pin there, and in between the two regulator ICs I've got a 12 volt one there, and there's a ground pin in that corner there. You'll also notice that I've also included now two heat sinks, small heat sinks on the power regulators, just to give some additional cooling. I did find that the 5 volt regulator was getting fairly warm as we've got more loading on that now. So adding a heatsink doesn't go amiss, and I've just put these small heatsinks on there. Here we see the reverse side of the PCB. You'll notice here I've got a few modifications I've made. There's a link there. I've had to cut a track, and there's a capacitor there which will be on the top side of the board. So I found in the process of building this I need to make a few little improvements to the design of the PCB. And on the final version, which I'll make available for you as a download, it'll have all those updates on, so you won't need any of this on the bottom. So that's the print side. Just pay particular attention when you're putting on the surface mount ICs, particularly the small ones there and down there, that you're not getting any of the pins shorting together. As part of the support for part 7 of this project, I've produced a drawing here which shows you the component layout for the component side of the PCB. This shows in detail exactly where all the components go. They're all referenced to the circuit diagram, and also I've got the links marked on here as well, and all the test pins. So that will be made available to you as a download. Any changes that I've made that I mentioned earlier, I'll also make on this as well, so when you do download it you'll get the latest version. Now, to go with the component layout, I've also shown here the print side of the board, and in particular the positioning of the surface mount ICs and the orientation of pin 1 with the little red dots. So this should help you when you mount the surface mount ICs on the board, and again this will be available as part of the download package. I've also done a separate drawing just showing the shorting links on the component side of the board with the print showing through from the back side. So this will clearly show you where you need to mount all the links on the PCB. I'll also provide a full schematic diagram for the whole project for part 7. All the components now are on a single schematic. I've grouped together relevant parts of the board and just highlighted it with dotted lines around each section. I'll just point out there we've got the negative 5 volt regulator circuit, and remember when I spoke about that I said that I finally decided to replace the ICL 7660 with a linear technology LTC 1046, and in that case we're not using the 100 PF capacitor, so C3 is not installed, and C4 and C26, which here are shown as 100 microfarads, we'll revert back to 10 microfarad tantalum capacitors. So I'll make some notes on the schematic on the version that you download. Before we go any further with this part 7 of the project, I just want to make a quick test that the new PCB is at least working. So I've quickly hooked it up to an LCD with the I2C module on the back. I've got the socket there plugged in for the voltage sense input. Keypad is plugged in. The rotary encoder I've got plugged in with the switch, and I've got the power or the load on off button plugged in, and the last one there is the socket there for the power input. What I haven't done so far is plugging anything to do with the trigger input circuitry or the fan. I just want to test that the unit, the new PCB at least, is working. So let's switch on and see if it springs to life. We now got version 27 of software, as you see there, and you'll recognise the display. It's like what we had previously, and nothing's changed there. So that seems to be fine. Let me just supply some voltage to it from a power supply. So I'll just switch on. It's just over 5 volts I've got coming in. So we've got 5.072 of a volt. You'll also notice that the current is actually down at 0 now. We haven't got any leakage current coming through. So that seems to be working fine. Before I do a full test and adjust the calibration, I'll just adjust the rotary encoder, make sure that works. So I can go on, yeah, I can alter the current. Pressing the button in on the encoder, we can move the cursor position, so that works fine. So I'll just set the current back to 0. Just make sure that the keypad is working. So if I put 1.2, yeah, 1.2 amps, that seems to be working. Let me just switch the load button on and just see that simple test what the reading we get out on the current reading there. At the moment we're getting 1.208 of an amp, and we've set it for 1.2 of an amp. So we haven't done any calibration on this at all yet, so that seems to be fine. And I think the next thing is we'll actually do a full test and we'll adjust the calibration. And I also want to check the temperature of the power MOSFETs at the output. Well, I think the next thing we're going to do, we're just going to do a test of adjusting these presets here on the board, just to see how we can calibrate those. And for that I've got it connected to a power supply which is set at the moment for 5 volts, and I've also put this meter here in series with the DC load, so we can monitor the current on that meter as well as on the power supply there. And then on the other side I've got another meter which is connected to the power supply the same way that the voltage sense circuit is from the DC load. So for the purpose of doing this, I've also left the matrix keypad disconnected. I haven't got the fan connected at the moment. This is just a preliminary test, and what we'll do now is we'll switch the DC load on. After its startup sequence, on the display there you'll see that we've got a voltage reading there of 5 volts, and you can see that matches quite nicely actually, with both the power supply and also with the voltmeter here. So I'm going to leave the voltage sense preset alone for the moment. But what you notice there is that we've got some leakage current. On the DC load it's showing as 0.007 of an amp. On the power supply it's showing as 0.043, and that's confirmed there by that meter, 0.043 of an amp, 43 milliamps. So what we're going to try and do first of all is null out that leakage current by adjusting RV3, which was the nulling preset that we installed on this update. So if I adjust that, and if we look at the current reading on the power supply and on the DC load, you can see the DC load is going down now to, it's on 1 there at the moment. You see the power supply reading, DC load is now showing 0, but we've still got a little bit showing on the power supply. So let me take it down, right down on the power supply, but be careful that you don't take it too far. Once you get down to around about 1, it's sort of flickering there. There I would stop. If you take it too far, then you would affect the reading later. So, oops, there. So if I stop round about there, that should be sufficient. The next thing I'm going to do now is then, using the rotary encoder, set the current to 1 amp, and then switch the load on, and then just monitor the current. Now you see the DC load is showing it as at 1.003 of an amp, whereas actually what we're getting there is 0.989 of an amp. That's confirmed by the meter there. So I'm going to adjust now the current set trim preset, which is RV4, and looking at the power supply current, I'm going to adjust this until we've got a reading of 1 amp. Take it up. There we go, just hovering there. 0.99. There we are, we've got 1 amp, just slightly over 1 amp. So that's we're now drawing 1 amp of current. You can see on the DC load it's actually showing 1.015 of an amp, so there's a slight error there, and I'm going to have a look at that and see whether we can trim that out in some other way, either in software or maybe some other hardware adjustment, but I'll come back to that later. Let me just turn the current up to 2 amps. And pretty close there on the power supply, it's showing us 1.997 of an amp, and the DC load is showing 2.019. Again, just a slight error there. Let's take it up to 3 amps. We're slightly down, as you can see there, on the power supply, and slightly up there on the DC load. So there's a slight adjustment error there that we need to address, and we need to have a further look at that on the DC load. But other than that, it does appear to be working. And the other thing I wanted to test, I'm going to just switch it down to 2 amps, and I just want to check what the heat distribution is across the 4 MOSFETs. And for that I'm going to lay the board flat down again, and I'm going to use a heat imaging camera just to have a look at those 4 MOSFETs and see how efficient our circuit is working on that. I'm now just monitoring the MOSFETs there on the heatsink there. Remember, we've got no fan connected at the moment. I'm drawing 2 amps, and looking at the heat imaging there, I can see they all look to be exactly the same in terms of heat distribution. So let me just zoom in on that, and you can have a better look. Well, I don't know whether you can see that too well, but looking at it here, I can see that the heat distribution across all those 4 MOSFETs is equal. They're all glowing equally the same, and we haven't got one sort of looking as though it's hotter than the other. I'll just go and check the temperatures of them quickly. They're all running at the moment at about 30 degrees. so that the current is very evenly spread across those 4 MOSFETs. So our little circuit appears to be working quite well. Well, I think I'm going to leave part 7 of the project there for today. There's a little bit more work to do yet in terms of finalising this and then fitting this into the existing project case. I still need to test all the functionality of this single PCB. I'm sure there's 1 or 2 little niggles that I need to sort out. But if you're interested in having a go at this, I will provide details of the PCB, the artwork for the PCB and the component layout, and I'll include that in a zip file below which you can download. And also included in that zip file will be all the details of the updates that I've discussed today. Now, as a result of this change, I've also updated the software now to version 27, and I'll give you that as a link as well. But I think the software is still work in progress because I think I want to make a few little changes there as well. But I'll keep you updated on that. In the meantime, thanks for watching, and if you found this of interest, please give me a thumbs up and subscribe. Bye for now.